All right, welcome back to Talk Tensors. We're always excited to jump into these deep dives with you.
Absolutely, always a pleasure.
And today we're going to be taking a close look at a paper that I think is really pushing the boundaries in a very interesting way.
Yeah.
The title is, it's a bit of a mouthful, but ReMA, Learning to Meta-Think for LMs with Multi-Agent Reinforcement Learning.
Yeah, lots of acronyms in there.
Yeah.
But it's a very intriguing paper, really gets at the heart of some of the big changes happening right now in LLM research.
Yeah, and I think for anyone listening who's been following the evolution of these large language models, you'll immediately recognize one of the key words that jumps out, and that's this idea of meta-thinking, right? And this paper really tackles that head on. It's not just about scaling models up anymore, making them bigger. It's about making them think smarter, especially when they're faced with a new problem.
Exactly. It's like we've hit this point where just throwing more data and compute at the problem isn't enough. We need to figure out how to make these models more reflective, more strategic in their reasoning.
Yeah, and that's where this idea of meta-thinking comes in. And for our listeners, just to give a quick definition, meta-thinking is essentially an LLM's ability to monitor and evaluate its own thought process. It's like having an internal editor or strategist, as we were saying before we started recording.
Yeah, it's like giving the LLM the capacity to step back and say, hold on, am I approaching this the right way? Is there a more efficient path? Should I re-examine my assumptions?
Right. And what's so fascinating, and I think what makes this paper particularly relevant, is that we're starting to see these glimpses of human-like meta-thinking patterns emerge in some of the most advanced LLMs out there.
Absolutely. We see it in models like OpenAI's latest, DeepSeq R1, and even more explicitly in something like Gemini 2.0 with its flash thinking. These models are demonstrating this ability to pause, to reevaluate, to come up with more nuanced solutions.
Yeah, and I think, just anecdotally, even for people who aren't necessarily deep in the technical weeds, they've probably encountered this. You're interacting with a really sophisticated chatbot, and it might say something like, let me think about that for a moment, or, perhaps there's a different approach I could try here. It's almost like they're engaging in this internal self-correction.
Right, and that's precisely what makes this area so exciting. We're seeing these hints of higher level cognitive processes emerging. And this paper, this ReMA framework, offers a really promising way to understand and cultivate those abilities.
Yeah, and to really dive into the specifics here, maybe we can start with the core of ReMA. What exactly does it introduce?
So the paper presents this novel framework called, as you mentioned, reinforced meta-thinking agents. And the central idea here is to leverage something called multi-agent reinforcement learning, or MRL, to explicitly encourage this meta-thinking within LLMs.
And for our listeners who may not be as familiar with multi-agent systems, can you break down how that works in this context?
Sure. The basic concept is to, instead of having a single LLM trying to do everything at once, we break down the reasoning process into two distinct agents that work together. We have a high-level agent, which you can think of as the strategist, and a low-level agent, which acts as the executor.
Ah, okay, that's interesting. So it's like a division of labor within the model itself.
Precisely. The high-level agent is responsible for the big picture thinking. It sets the overall goals, it devises high-level plans, it decides which reasoning paths to explore, and then the low-level agent takes those plans and actually executes the detailed reasoning steps to solve the problem.
So if we were using this to, say, tackle a complex math problem, the high-level agent might choose which theorems to apply, and the low-level agent would then carry out the actual calculations.
Yeah, that's a perfect analogy. The high-level agent is like the mathematician who's mapping out the strategy, and the low-level agent is like the calculator doing the grunt work.
Right. And what's the advantage of having this kind of separation, this two-agent system?
Well, there are several key benefits that the paper highlights. First, by separating these processes, the system as a whole becomes much more adaptable. Each agent can specialize in its role, leading to better exploration of the solution space.
So it's not just about thinking smarter, it's about exploring the problem more effectively, considering a wider range of possibilities.
Exactly. And this really shines through in the results. The researchers tested ReMA on some pretty demanding benchmarks, including challenging mathematical problem-solving tasks, and these LLM as a judge benchmarks, where one LLM has to evaluate the output of another.
Oh, that's interesting. It's like having a peer review process built into the system itself.
Yeah, exactly. And what they found was that ReMA consistently outperformed single-agent reinforcement learning methods on these tasks. The two-agent system led to more robust reasoning, better generalization to new problems, and an overall higher quality of output.
And it seems like this idea of separating meta-thinking from the actual reasoning steps ties in really nicely with this trend we're seeing of increased test time computation.
Absolutely. One of the big takeaways from recent advancements in LLMs is that giving these models more time to think, to deliberate during inference, leads to significant performance gains. And ReMA is inherently designed to capitalize on that.
Because it can essentially explore a wider range of high-level strategies and then dive deeper into each one before settling on a final answer.
Exactly. And this mirrors what we're seeing in those cutting-edge models that are allowed to do more computation during inference. It suggests that this meta-thinking component is crucial for unlocking the full potential of these systems.
Yeah, it's really quite remarkable to think that something that we long considered a uniquely human cognitive ability, this metacognition, might be emerging in artificial intelligence as well.
It is quite profound when you think about it. And it really raises a lot of interesting questions about the nature of intelligence, about the future of AI, and about the relationship between human and machine thinking.
Absolutely. Now, to fully appreciate the significance of ReMA, I think it's helpful to understand what came before it. What were the main approaches to improving meta-thinking in LLMs prior to this paper?
So the paper outlines two main lines of research that preceded ReMA. The first was what they call construction-based supervised approaches. And the idea here was to create data sets of reasoning processes that explicitly demonstrated meta-thinking.
Okay, so like providing examples of how a model should ideally approach a problem, including those self-correction steps, the planning stages, and so on.
Exactly. They would create these structured reasoning trajectories, and then they would fine-tune LLMs on these data sets using methods like supervised fine-tuning or SFT or direct preference optimization or DPO. It was essentially teaching by example.
Yeah, that makes intuitive sense. So what were the limitations of this approach? Where did it fall short?
Well, the main problem was a lack of flexibility. Because these methods relied on a fixed set of predefined templates and reasoning structures, the models struggled to generalize to problems that didn't fit those patterns.
So they might be good at mimicking the specific types of meta-thinking they were trained on, but they wouldn't be very creative or adaptable when faced with something new.
Exactly. And that led to a noticeable drop in performance on out-of-distribution problems, those that deviated from the training examples. The models just weren't very robust or reliable in novel situations.
Okay, so that's one approach. What was the other line of research that led up to ReMA?
The second approach involved single-agent reinforcement learning, or SARL. And here, the idea was to use reinforcement learning techniques to directly train a single LLM to exhibit meta-thinking behaviors as part of its reasoning process.
So instead of explicitly providing examples, you're essentially rewarding the model for exhibiting those desirable behaviors.
Exactly. The model would receive rewards based on the quality of its final answer, and sometimes on the intermediate reasoning steps as well. It was more about guiding the model towards those meta-thinking patterns through a system of rewards and penalties.
Got it. And what were the main challenges with this SARL approach?
Well, there were a few key obstacles. First, it often required either exceptionally strong foundational models to begin with, or a lot of very task-specific fine-tuning to get stable training. And that's because the model was being asked to learn both the high-level strategy and the low-level execution all at once.
Right. It's like trying to teach someone to be both the CEO and every department head of a company simultaneously.
Yeah, it's a lot to ask. And because of that, exploring the vast space of possible reasoning strategies became incredibly inefficient. And it could also make the reasoning process less transparent and lead to the model converging on suboptimal solutions.
So it might find a solution, but it might not be the best or the most elegant one, and it might be hard to understand how it got there.
Exactly. And that's where ReMA really steps in and addresses those limitations. By introducing this multi-agent framework, it separates the meta-thinking from the reasoning, making the learning process much more structured and efficient.
And just to clarify, the paper explicitly points out that this is a novel approach, right?
Yeah, they emphasize that, to the best of their knowledge, ReMA is the first work to formally define and optimize this multi-agent meta-thinking reasoning process, which they call MMRP, through multi-agent reinforcement learning.
So it's not just a new application of existing techniques, it's a fundamentally new way of thinking about how to cultivate meta-thinking in these models.
Right. It's a significant contribution to the field and opens up a lot of interesting avenues for future research.
Absolutely. And speaking of future research, the paper also touches on some really intriguing potential extensions and open questions, particularly in Appendix A. Maybe we can dive into some of those novel notions.
Yeah, Appendix A gets into this really interesting idea of scaling the MMRP framework at inference time.
And this is where the computational cost considerations really come into play, right?
Exactly. Because ReMA has these two agents, the total computational cost during inference, measured by the number of times the model has to generate outputs or samples. Depends on how much sampling you do for each agent.
Right, because if the high-level agent generates, say, K1 potential plans, and then for each of those, the low-level agent generates K2 reasoning steps, then the total number of samples is K1 times K2.
Right. So if you want to explore a wider range of possibilities, if you want to do more thinking, you're going to need more computation.
And that raises this very practical question of how to optimally allocate your computational resources.
Exactly. If you have a fixed budget for inference, should you prioritize exploring a wider range of high-level strategies by increasing K1, or should you focus on getting more detailed and refined execution for a smaller set of strategies by increasing K2?
It's a really interesting optimization problem, especially when you start thinking about real-world deployments of these models.
And the paper doesn't provide a definitive answer, but it lays out the problem and suggests some potential directions for future research.
Right. It's more about highlighting the trade-offs and encouraging further investigation.
Exactly. Another interesting aspect they touch on in Appendix A is the question of how to re-rank the final outputs that are generated by this two-agent system.
So you have all these different potential solutions. How do you decide which one is the best?
Right. And they introduce two main strategies. The first is what they call hierarchical re-ranking. And this involves first evaluating and ranking the low-level reasoning outputs that correspond to each high-level meta-thought, and then comparing the top-ranked outputs from each high-level plan to arrive at the final best answer.
So you're essentially maintaining the connection between the strategic thought and its execution when you're assessing the results.
Exactly. The second strategy is called flat re-ranking. And here you just pool all the sampled reasoning outputs from the low-level agent, regardless of which high-level plan they came from, and then you rank them all together based on some evaluation metric.
So in that case, you're just looking at the quality of the final output, regardless of how the model got there.
Right. And they suggest that the optimal re-ranking strategy might depend on the specific task and the nature of the meta-thinking involved.
Yeah, it makes sense that there wouldn't be a one-size-fits-all solution here.
Absolutely. And again, they point to this as an area where further research is needed.
Well, I think this has been a really insightful deep dive into the ReMA paper. Maybe we can just quickly recap the key takeaways for our listeners.
Sure. So ReMA introduces this groundbreaking multi-agent approach to fostering meta-thinking in LLMs. And the results show that this approach leads to significant improvements in performance on challenging reasoning benchmarks.
And the core innovation, the separation of meta-thinking and reasoning into two distinct agents, seems to be really key to its success.
Right. It allows for more effective exploration during training and also provides greater transparency into the model's reasoning process.
And the paper also highlights the importance of careful reward function design and the potential for unexpected emergent behaviors like role reversal between the agents.
Yeah, those ablation studies were really fascinating. They showed how subtle changes in the training process can lead to significant shifts in the agent's behavior.
So it's not just about the architecture, it's about the entire learning environment.
Exactly. It's a complex interplay of factors that determines how these systems evolve.
Well, to leave our listeners with something to ponder, I think the big takeaway here is that ReMA demonstrates the power of separating cognitive processes within AI. And it makes you wonder what other complex AI capabilities could be enhanced by adopting similar hierarchical, multi-agent architectures and reinforcement learning techniques.
It's a really exciting prospect, and I think the exploration of multi-agent systems and meta-learning is going to be crucial for pushing the boundaries of AI in the years to come.
Absolutely. Well, thanks for joining us on this deep dive into ReMA. Until next time, keep those neural networks firing.